Well, thank you very much, Luciana and Christiana, for organizing this symposium. So last night, I couldn't really sleep. I'm kind of jet lagged, and I was thinking about what Kai had said about orbits. And I was thinking in what orbit I am, what Frei Otto orbit I am. And I think I'm like in the third or fourth orbit or something in between, but then Kai told me you could be anywhere really. So my link to Frei Otto is that I studied at the University of Bath with many of the Buren Happold people. So for example, Ted Happold was my teacher, Michael Dixon was my teacher, Ian Little was my teacher, my PhD advisor was Chris Williams. And so when I was a student at Bath, they had the enormous IL collection of books, and it wasn't the time of Instagram. So when I wanted to kind of get inspiration, I would go to the library, and I spent many times looking at all the books. And but you were saying earlier about ideas, stealing ideas. I will talk about that a little bit as well. Things that have kind of occurred. But anyway, I am in the United States now. I moved there about 15 years ago with my family. And this is a picture of highway route number 1. This is a picture that I've taken from the car when we're going to the seaside, because Princeton is very close to the Jersey Shore. What always strikes me is that these bridges are very massive. I used to before, I was at Princeton University, I worked for Ney and Partners, who does very elegant and beautiful bridges. And so this is a bit of an eyesore to me, because the construction industry is one of the most resource-intensive industries, and I just know that if you design them as simply supported beams, they would kind of look more like that, and you would save a lot of materials. When you get to the Jersey Shore, and actually this is not the Jersey Shore, this is Rockaway Peninsula at New York, this is kind of what that looks like. Lots of people having fun, and that's also what we're seeing. Lots of urban populations are moving to cities near the coast, and you have buildings very close to the coastline. In 2012, I was actually here in Stuttgart with Princeton students, and we couldn't return to Princeton because Hurricane Sandy had hit. And so this is a picture of Hurricane Sandy, New Jersey shore. And you see that this is actually a storm surge hitting buildings that are right next to the shoreline. This is not a rendering, this is picture real life. $70 billion damages, 650,000 houses destroyed, and many lives were lost. This is what happened right after the hurricane. People just went back to building the boardwalks, because the boardwalks are very important for attracting tourism. And so they were just restoring the boardwalks as if nothing had happened, as these storms would never happen again. But of course, this is a disaster waiting to happen again. Other villages or cities, like this one here, Big, which is actually where Kim Clijsters lives, they build a huge wall. The idea is if you build a huge walls with stones, that will be very strong and keep out the storm surge. So what are the research questions that we're tackling in my research group? First of all, what is the relationship between form and efficiency in structures? Very much in tune with this institute. And also then, more specifically, how can we use mechanics, methodology, and design innovations to transform the way that we build from massive to lightweight and force modeled, and then achieving a built environment that contributes to our quality of life. And of course, I am not the first. I have my lab is called the Form Finding Lab. Obviously, I'm not the first one to think of forms. I have here a graph, and on the x-axis we have time, on the y-axis we have weight, and notice that that's a logarithmic scale. And you see that throughout history, people have been using forms. We have the pyramids at the top, form very massive. Then, we have the Hagia Sophia, we have the Chinese bridges, we have the Gothic cathedrals. And then more recently, we have very lightweight structures. And I put Frei Otto's membrane in Castle there as well. I also put a line at the 1 kilonewton per meter squared. That is the load of a good wind. And this wind can either go down, pressure, or it can go up. And so if you don't design your lightweight structures well enough, they can actually lift up. And also, Mick, for you, that one there is the Dutch Marine Museum that I worked on. I worked on the form finding when I was working for Laurent. Okay, so what do we need to do? I think we need to change what we design, how we design, and how we build. So what we design, so I'm very interested in slender surfaces. That means surfaces that have one dimension much smaller than the other dimension. In particular, I'm interested in shells, flexible and rigid shells, nets and membranes. We have to use geometry and mechanics, and this is of course very challenging with slender surfaces because they are non-linear. They have, many properties that are actually quite difficult, and I will talk about that a little bit more later. And also we have to change the way we build, because about 39% of waste in landfills comes from the construction industry. And we have many challenges. I'm just going to mention a few. One is, and I'm putting this up because I know this is all very obvious to you, but sometimes when I give talks to other engineering audiences like electrical engineering, they are not aware that we build at the very large scale, 10 to 100 meters or 1,000 meters. That means also that some of the structures that we use, cannot just be scaled up. And Galileo already knew this. Temporal scale. We work at a very long temporal scale, right? So we're not like, if we design an iPhone, it will last 2 years, 5 years. Mine lasts 10 years because I'm kind of taking very good care of them. But, the things we build are 50 years, 200 years, 2,000 years. I'm going to talk about that building again. And then the materials that we have available are also much more limited because they have to last 200 years. And so, for example, we have talked about nature, but nature has a much wider palette of materials available, but its structures don't have to last 50, 100, 2,000 years. So these are all challenges that you're well aware of, but that kind of really put big constraints on the things we do. And so, yeah, this is me. We're going to talk about, I call it extraordinary mechanics of slender structural surfaces. So these surfaces are very thin. They are non-linear, even if their materials exhibit linear behavior. So that means that they can have properties that other structures do not have. Beam and column structures do not have these properties. And I'm going to show how I'm going to show some of our work where the first one I'm going to show about how these things can morph or change from one shape in another shape to, for example, guide airflow. I'm going to talk about how, if we look at form finding, so basically a process that tells you where the forces are, if we use that very carefully, we can actually increase the load capacity of, in this case, rigid shells dramatically. I'm going to talk about how we can construct without any scaffolding. So I call this imperceptible self-locking construction. So basically the forces in the construction are supporting the construction while we are building it. And finally, I'm going to talk about how we can imagine deployable storm surge barriers that are pressurized membranes in which we can tune their stiffness, and where we're actually balancing a fluid inside the membrane with another fluid outside the membrane, the storm surge. So I'm going to go talk about the first one first, which are the flexible shells. And the title of my talk, I didn't really say that, but it's something like defined by forces, but framed for humans. So the first project I'm going to show relates to cities and actually came about in COVID. So the idea is that if you look on the right-hand side, we see how in these squares or buildings, if we have airflow, if the buildings are quite far apart, the airflow will kind of move air between buildings. But as your buildings, that picture there, get closer together, the air actually gets trapped. And this is very bad for COVID or air particles to move. And so you will see that in all the 4 projects I'm going to show, the reason we're doing this is to help people. So what we're trying to do here is to improve ventilation so that, for example, COVID doesn't really get trapped here, or that's a picture from New York, what they were doing. During COVID, you could go and eat there, but of course there also the air particles get trapped, and also provide shade. And for this project, we get our inspiration from kirigami. Kirigami is the Japanese art of having a flat piece of paper, make cuts in it, and then when you pull it apart, these cells buckle and rotate. This is really good because it's very simple. It's a flat sheet. You just make cuts in it. There is no construction waste whatsoever. It's very easy to transport because you just pack all the sheets on top of each other. The question is, how do you translate this to a canopy that is going to move air about? So we have a number of tricks up our sleeves. We have, on the first, we have experiments. And I was thinking this machine would fit very well here, kind of thing. So this is a box with this kirigami in it. It's also positioned here. This machine here is a machine. It's called a particle image velocimetry. And basically, we put our box here. We let air come in here. We have this laser, and we can actually take pictures. And these are the pictures that we're seeing. We're seeing that in the first vent here, the air goes down, and then it kind of moves up and moves the air outward. This is a finite element analysis to do the kirigami buckling, and then it's coupled with fluid dynamics at large eddy simulation, and we're seeing that our experimental results and the numerical results match very well. And so what we're seeing is that the air goes in and then picks up whatever is in the box and then goes basically back out. Of course, kirigami, you can actually, it's bistable, so you can actually switch it, right? So you could have all your louvers in this direction, or you could have two in this direction and one this direction, or you could have one in this direction and two in this direction. And so basically what we're showing here that with all these different variations, because your wind could either go from left to right or from right to left, you can actually control the wind. So that's very lovely, but this is a very tiny experiment. Another thing, sorry, I forgot. You can actually tailor the cutting pattern so that some of your vents go up and some of your vents go down. And that's a function of your length of your cut, as well as the position of each other, as well as length of your cut and how far they are apart, right? So we can have vents going up and vents going down. This is a tiny model. How do we upscale this for a large thing? And so we just come back from Venice, where we actually made a first prototype. It's the prototype and immediately on display, where we have a large, so it's a steel frame. It's about 3 meters by 3 meters by 3 meters. It is a sheet that has this cutting pattern here. It is suspended, as you see, from the steel frame and is actuated by a motor there. And it basically opens and closes and controls the airflow in the system. Okay, that was flexible shells. I'm going to go quickly. I'm now going to talk about rigid shells and form finding. So basically, we kind of realized that throughout history, many shells kind of survived very big extreme loads like earthquakes, tornadoes, hurricanes, while all the other structures around them collapsed. And so we were curious to see how this worked. So we looked at Felix Candela's church in Mexico City, because there was a huge earthquake in 1985, 8.5 on the scale of Richter. This church showed, and as many of other Felix Candela's structures, showed very little damage. So we're interested in what is it in these structures that these shells don't experience any damage or hardly any damage under earthquakes. So we carried out dynamic analysis to, well, first of all, see the stresses under earthquake loading, very low. I already knew that. But also to see what the eigenfrequency is. So we found that for this particular shell, 42% of the mass contributes to the eigenfrequency of 3.09 hertz. That is a very high eigenfrequency compared to, for example, beam and column structures. And the peak of the Mexico City earthquake was at 0.5. So basically the earthquake and the structure, their frequencies didn't coincide. If you have two frequencies coinciding, you get something what is called resonance, and that's when very large damage occurs. So we were interested, how come these shells have such a high frequencies? This is not the only formula in my presentation, but one of the very few ones. Okay, so the definition of eigenfrequency is a square root of stiffness over mass. Okay, we're talking about shells, mass very small, because very small thickness. Case stiffness. Well, the stiffness of these shells is actually very high because it has what we call geometric stiffness. It means because they are curved, this number is very high. And that's why you get very high eigenfrequency, which does not coincide with the low frequency of the earthquake, and you don't actually get any damage. So great. How can we use that to define new structures? We started by defining arches, and we use the graphic statics method. So basically, this is a graphical form-finding method where you draw the forces, the blue is the self-weight, and then we added to it the horizontal, about 0.3 of the self-weight. We added that vertically, and we end up with a truss line. So basically, Mosley said that as long as that green truss line lies within the thickness of your arch, you don't get any hinges developing, and your structure doesn't collapse. And so we end up with this truss line, the green truss line, but of course the earthquake can go from left to right or from right to left, so we mirror image it. And then we kind of offset it and define an envelope through that. And so basically, according to our thinking, this would be an arch that under 0.3 G would not collapse. We then, when I studied in the 90s, my PhD, people would have said, well, you cannot actually build an arch like that, but now with 3D printing, you actually can. Okay, so then we kind of divided this into voussoirs and kind of did a limit state analysis to kind of verify under which conditions and under which hinges this arch would collapse. And we found indeed that under 0.3 G, this arch collapsed. So that's exactly the one that we had found that shape for. Now, we don't build arches anymore. We are actually maybe more interested in shells. So we do the same thing, truss line, mirror image it. Now, instead of defining the envelope, we offset it with half a period. We loft the surface through it, and we end up with this shell shape. So the question is, okay, is this good at taking earthquake loads? And you might have never seen a shell like that. Actually, Eladio Dieste, 1978, built this kind of shells. His shell is different because his corrugations go all the way through, and the corrugations at the base are, in his case, mirror imaged. In our case, they are parallel. So they're slightly different, but we use Eladio Dieste's shell as a case model, and we carry out parametric studies. So same span, same height, same amount of material, only the corrugations are different. Period is different, and the depth. And so we carry out a nonlinear pushover analysis. So that's basically you're pushing, this, well, there's self-weight, you're pushing from the side. At some point, a crack starts occurring, but you keep on pushing. You adjust your concrete model because you get cracks in it until four hinges occur, and then your shell collapses. So we see all of them develop 4 hinges. That's great because it behaves like an arch. But the location of these hinges is different. Either they're on the sides, like in this one, so in FF1, let's see where else, FF5, or it occurs at the top. FF2, FF3 has like one occurring at the crown. And the reason for that is because this is kind of the geometry of these shells. These cracks occur at the position where they are singly curved. So this geometry is mostly doubly curved. In some locations, it's singly curved. That's where it's the least stiff. That's where it will attract the forces, and that's where you get your hinges occurring first. Okay, so we do this pushover analysis to see the ST shell. Okay, it's very light. Okay, at 0.2 PGA, a crack starts occurring at 0.3. This is like what earthquake loading, it will collapse. All these shells perform better, especially this one here, the FF3. So that is one where you have a very small period, quite deep corrugation depth. The first crack starts occurring at about 0.38 PGA, and it collapses at 0.57 PGA. So much bigger than this one here. Meaning, wow, same amount of material, same span, same height. The only thing we've done is change the corrugations, and we get much, much, much better performance. And so I think that is really fantastic. This is really using form to, in this case, increase stiffness and load-bearing capacity. And this is, a rendering of how this might, what this might look like in San Francisco area. we all know that shells actually are not that much built anymore, except for iconic buildings like the Stuttgart train station. And so one of the reasons why they're not built is because this is how Felix Candela built them. He actually built two structures. He built this one, then he built the other one, and when that one had cured, he took this away, right? And a lot of it ends up in the landfill. Okay, so basically, it's estimated that 40% of the project cost is in the scaffolding. And so we were interested in, can we build this without scaffolding? So I'm going to talk now about self-locking construction, and I'm going back to one of my favorite structures, which is the Santa Maria del Fiore dome in Florence. And this is work with a PhD student that came from the University of Bergamo, Vittorio Paris, who wanted to know how this dome here, it is in literature, it's said that this dome was constructed without scaffolding. So this is passed down in literature, but nobody has ever proven how this could have been possible. We have drawings like this one here. This is a plan view. This is a section. In the plan view, you see all the horizontal courses. You have these vertical ones. You see in section is actually two domes, but of course we're interested, how do we build the inner dome? Because then we can use that as scaffolding for the outer dome. These spirals are interested in these Italian Renaissance domes. Sometimes they go up one way, sometimes they go up two ways. People say they're decorative, but actually often they're covered by frescoes, so probably not decorative. And so we started to having a hunch that these vertical bricks maybe have something to do with how you can construct this without scaffolding. And so we built a model. This is an octagonal dome. And we coupled parametric modeling to discrete element analysis and put every single brick to see what's happening. And basically what's happening, well, we made a couple of assumptions. First, we assumed that these domes were constructed radially, right, like an igloo. And then also that they were kind of, in the end, you know, first you start building, it's a bit like building a wall vertically upward, but then they start curving inwards. And so what we found is that these vertical bricks, they are fixed into the layer below. And what we found is that when you put these horizontal bricks in them, they will kind of slide inwards. And what happens then is once they slide inwards, they actually jam against the vertical bricks and kind of get stuck. And so when they jam against these vertical bricks, there's a huge force. They call it plate bond mechanics. So it's basically a flat arch developing in here. That flat arch pushes very hard against this vertical brick, which then transfers these forces into the layer below and into the layer below, et cetera, et cetera. And so that's kind of probably how these domes could have been built. You see here a still from top right that is for bricks with no friction between them. It's basically they're Teflon coated, which is not possible. But at the bottom, you see from the moment that you have friction angle of about 10 degrees, in masonry it's usually 15 to 20 degrees, these bricks get stuck. And so we kind of proved that you can actually construct an entire dome like that. So this was our flow chart, you know, first checking, do the bricks slide, yes or no? Does the thing fall over? What are the forces in the layer below? And then checking whether your meridial and your hoop stresses stay within your dome. So that's all. I have 1 minute left. Oh, okay, I'll go very quickly. So how can we use this today? And I will skip some here. So we worked on a project also for Venice, where we built this compression arch. And we used, again, this herringbone pattern to build this arch without supports. We use, of course, it's very difficult, and Arnold will notice, to describe to a mason how he has to position every single brick, because this is a complex curved surface. It's possible if you build like this, you can describe every point with X, Y, Z. If you live on Earth, you will say latitude and longitude, but if you have a complex curved shape like that, it's very difficult. Yes. So actually we use augmented reality. So basically our masons in Venice were wearing augmented reality to construct this. I'll just go over this quickly. Okay, this is the final project. You see the herringbone bricks in there. And now I'm going to go very quickly. I'm going back to the beginning of my story where I started talking about storm surge barriers, and I started imagining how could we use inflatable structures at a scale of 10 meters diameter. They have storm surge loading on one side, so that means there's static loading, there's wave break loading, there's dynamic loading. This is a rubber-coated nylon, so the material is non-linear, elastic, and so we started doing finite element analysis to kind of check what are the stresses, is there resonance, is there any, what are the displacements, and we found that, you know, for the Sandy storm that we had witnessed, that such a structure could actually resist this. Now, when I did that, and I was looking that up, here we're doing some experiments, I found that, of course, Frei Otto had already done this. He has done experiments with big inflatables filled with water, not so much for storm surge loading, but for other loading. Okay, so in my research, I look at what I call exceptional or extraordinary mechanics of force modeled structural surfaces. It was for a future-oriented environment. I look at how these surfaces interact with the environment. We draw our inspiration from biology, performance craft, and history, and we develop numerical, machine learning, graphical, and analytical methodologies to generate knowledge. And I want to show, I know I am completely run out of time, but I think this is a little present. This is a project I worked on. I am working on, if it's, I don't start. So, what we have talked about is spatial experiences. When that was first shown like in March this year at Princeton University.